Somewhere inside a vault in California sits a fuel pellet smaller than a grain of rice. It took millions of dollars and decades of physics to build, and for a fraction of a billionth of a second, it became hotter than the center of the sun. That moment happened at 1:03 in the morning on December 5, 2022, inside the National Ignition Facility, a laboratory most Americans had never heard of until that week. There is an old joke in physics. Fusion energy is 30 years away, and it always will be. For 70 years, that joke held, repeated by scientists, journalists, and skeptics alike, in almost the exact same words every single decade. Building a star inside a building on Earth and getting more energy out of it than you put in was simply too hard. That morning, at least for one fleeting instant, the joke finally died. To see why that night mattered, you have to see the mountain scientists were climbing. For generations, fusion was the punchline. Billions of dollars spent, decades of research, and the finish line never seemed to move any closer. So what exactly is fusion, and why has it been this hard? Every second, the sun crushes hydrogen atoms together under unimaginable pressure, fusing them into helium and releasing staggering amounts of energy. That is fusion, the same reaction that powers every star in the sky. The 70-year dream has been to build a star in a bottle here on Earth. Clean, almost limitless energy made from a fuel found in ordinary seawater. This is not the nuclear power already running today. Existing reactors use fission, splitting heavy atoms like uranium apart, and that process leaves behind waste that stays radioactive for thousands of years, along with the accident risks that have shadowed the entire industry since Chernobyl and Fukushima. Fusion is the mirror image. It joins light atoms instead of splitting heavy ones and produces almost no long-lived waste. It cannot melt down either. If anything goes wrong inside a fusion reactor, the reaction simply stops on its own, because unlike fission, there is no runaway chain reaction waiting to escape containment. On paper, fusion beats fission on almost every axis that matters, which is exactly why it has been such an obsession for 70 years running. So back to that night. Inside the National Ignition Facility, 192 enormous lasers fired at that rice-sized target. They delivered 2.05 megajoules. The fusion reaction that followed released 3.15. For the first time in human history, a controlled fusion reaction gave back more energy than was poured into it. Scientists call this ignition. For a brief moment, the energy coming out of the fuel beat the energy the lasers put directly into it. A genuine, measurable gain, the exact milestone the field had chased for 70 years. Headlines called it the birth of clean fusion power. The real story was more complicated than that. Before celebrating limitless clean power, look closer, because there is a catch hiding in the numbers. Yes, the reaction produced more energy than the lasers put into the target. The problem is everything upstream of that target. Those lasers are wildly inefficient, converting only a small fraction of the electricity that reaches them into usable light. To deliver 2 megajoules directly to the pellet, the facility had to pull roughly 300 megajoules from the electrical grid. The physics gained energy. The machine as a whole still consumed about 100 times more than the reaction ever released, and that gap is exactly what every serious fusion company on Earth is now racing to close. And the scale of the machine is staggering. The target chamber at the National Ignition Facility is a steel sphere weighing 130 tons, sitting inside a building the size of 3 football fields, all built to fuse a pellet smaller than a grain of rice. Walk the halls and you pass control rooms, laser bays, and cooling systems that took a decade to construct and cost billions of dollars, funded largely to keep America's nuclear weapons stockpile certified without live underground testing. This was never meant to be a power plant. It was a physics experiment built purely to prove the reaction was possible, and it worked. If the physics is proven, why not build a plant tomorrow? A real power station needs 3 things this experiment does not have. First, lasers efficient enough to sip electricity instead of guzzling it. Second, repetition. A working plant needs to fire something like 10 times every second. This facility fires only a few times a day. Third, materials tough enough to survive years of relentless bombardment from the reaction itself. None of these 3 problems are physics anymore. They are engineering, and engineering is a different kind of hard. There's not one way to trap a star, there are 2, and the entire industry is split between them. The first is magnetic confinement. Engineers build a donut-shaped chamber called a tokamak and use enormous magnets to squeeze hydrogen plasma into a ring so hot the atoms have no choice but to fuse. This is the older, more established approach, the one most national research programs bet on for decades. The second is inertial confinement, the approach the National Ignition Facility used. Fire lasers at a tiny fuel pellet from every direction at once, compressing it so fast and so violently that it ignites before it can fly apart. Both approaches work, at least in bursts. Neither is easy to run continuously. The race now is to engineer either one at real, sustained commercial scale. And there is the fuel itself. Fusion runs on two isotopes of hydrogen, deuterium and tritium. Deuterium is the easy half. It can be pulled straight from ordinary seawater, and the oceans hold enough of it to power civilization for millions of years. Tritium is a much harder problem. It is radioactive with a half-life of just 12 years, so it barely exists in nature at all. Fuse one deuterium atom with one tritium atom, and you get a helium atom, a stray neutron, and a burst of energy. Pound for pound, that fuel releases several times more energy than fission ever can, from two of the most abundant light elements in the universe. That single equation is the entire reason 70 years of physicists never gave up. The entire world supply of tritium is estimated at roughly 25 kilograms. A single commercial fusion plant might need several kilograms of it every single year. So reactors plan to breed their own, wrapping the reaction chamber in blankets of lithium that convert into tritium as the reactor runs. Nobody has actually built a working breeding blanket yet. Solving that is not optional. It is existential for the entire industry. The United States is not racing alone. This chase spans 70 years and 3 continents and reads almost like a relay race between rival nations. The first tokamak fired up in the Soviet Union back in 1958, a design so effective that most of the world's reactors still copy its basic shape. In 1997, Europe's jet reactor set a fusion power record that stood for a generation, a benchmark nobody could beat for 25 years. In early 2022, jet finally broke its own record for sustained energy output. Then that December, California achieved ignition and has repeated it since, with higher yields each time as engineers refine the target design. In Germany, a machine called the Wendelstein 7X takes a completely different path, twisting magnetic coils into fiendishly complex shapes to trap a stable, continuous loop of superheated plasma. It is one of the most geometrically complex machines ever built, requiring computer modeling that pushed supercomputers to their limits. And in Japan, the JT60SA, the largest operational tokamak on Earth, recently achieved its first plasma after years of delay. Every one of these machines is a different bet on the exact same prize. But if you want the single moment that unlocked the private fusion gold rush, it was not December 2022. It was September 2021, when a team at MIT switched on a new kind of superconducting magnet and hit a field strength of 20 Tesla, far beyond anything achievable at this scale before. Magnet strength sets how small a reactor can physically be. 20 Tesla was the number that changed the math. With conventional magnets, a working reactor needs to be roughly the size of ITER, the 35-nation megaproject under construction in France. With these new superconducting magnets, the same reactor can shrink toward the size of a garage. Smaller means cheaper to build, and cheaper means private money can finally compete with government megaprojects that take decades to finish. Here is the truth the hype conveniently forgets. Even if every one of these engineering problems gets solved, a fusion power plant still runs on a 1920s idea. The reaction makes heat, the heat boils water into steam, and the steam spins a turbine exactly like a coal plant. What changes is only the fuel. It still just boils water, only the fuel changes. This is where December 5th really changed things, and not inside the lab. Capital follows proof, and ignition removed the deepest risk investors had always priced in, proof that the underlying physics actually works. For decades, investors avoided fusion entirely, treating it as a bottomless money pit with no visible finish line. The moment ignition landed, the question flipped. It stopped being will fusion ever work and became who builds a working reactor first. Look at where the money actually went. For years, private fusion investment crept along quietly, $1 billion here, $1 billion there, mostly from a handful of true believers willing to fund decades-long bets. Then 2022 happened. In the 18 months after ignition, private capital nearly doubled, climbing past $7 billion total, an amount that would have sounded like science fiction to the field a decade earlier. Dozens of startups now compete worldwide, no longer racing to prove the underlying science, but racing to win the engineering war and reach the grid first. The contenders are moving fast, and each is betting on a different design. Commonwealth Fusion Systems, an MIT spinout, is building a compact reactor around those new high-field magnets, aiming for genuine net energy this decade. Helion has already signed a deal to sell fusion electricity directly to Microsoft. Others, like TIE Technologies and Tokamak Energy, are chasing entirely different reactor geometries, betting that a different shape of magnetic bottle solves the engineering problem faster than the mainstream approach. This is not a science project anymore. funded by government grants and academic curiosity. It is a hyper-competitive industry, with real customers, real venture capital, and real deadlines attached to actual contracts. Helion has promised real fusion power onto Microsoft's grid by 2028. Whether or not that exact date holds, a major corporation signing a commercial fusion power contract at all would have been unthinkable just a few years earlier. The timeline has genuinely, measurably shifted. Though how far away is fusion, really? The honest answer is that the question itself has changed shape. For 70 years, how far was a physics question, and the only honest answer was a helpless 30 years, forever out of reach, no matter how much money got thrown at it. Now it is an engineering and a capital question, the same kind of question that once faced commercial aviation or the internet or reusable rockets. And engineering problems, unlike genuine physics mysteries, eventually fall to money, talent, and enough time. For the first time, 30 years is a schedule, not an excuse. We are entering the engineering era of fusion power. The lab proved the physics. The next decade will prove the business. If a piece of technology has ever seemed permanently 30 years away to you, tell me which one in the comments. Every week on Second Order, we take apart another system that isn't quite what the headlines made it sound like. Thanks for watching.